invitees and students who have joined today's seminar. So as you know, we have been conducting these talks uh, over the past 1.5 years with the primary objective of educating our members and students on various topics in physics and related subjects, apart from what they normally would have studied. So this is some kind of a continuing education program, which universities and colleges should really be taking up. Unfortunately, they are not doing that. And we are very glad that we have been able to provide that particular need in terms of physics, at least. So we've been connecting teachers and students all over Karnataka with variety of topics, right from quarks all the way to cosmology, so that they would be benefited in their teaching and research also. So with that view in mind, we have been conducting these programs, and we have also conducted talks in Kannada. We are encouraging with the view of definitely encouraging the usage of the local languages in science and technology, just for the benefit of students and teachers. Ultimately, maybe we have to do that. Most of the people are not native speakers of English, so it would be nice if we can do the higher education also in the local languages. But we are very far from that ideal situation. So we are doing our bit to encourage the usage of local language Kannada. So today we have a distinguished speaker, Dr. Ajit Singh from Prayoga, research scientist at Prayoga. He will give us a talk about a very interdisciplinary subject. This topic involves physics, chemistry, biology, geology, everything, all sciences put together, environmental science, climate change, and so on. So that will be very beneficial to a lot of people in the audience, I would suppose. So before I request him to talk about this topic, the terrestrial water cycle through a river system, I request our Joint Secretary, Dr. Rudaswamy, to give a brief introduction to his academic career. Professor Rudaswamy. No, unmute, you're muted. Unmute. Unmute, we are not hearing you. Okay.
Good morning to all. Thank you very much, sir, for the opportunity. It is indeed a great honor and immense pleasure for me to introduce today's eminent speaker, Dr. Ajit Singh, who speaks on the terrestrial water cycle through a river system, which is a subject of earth science. I am proud to say that Dr. Ajit Singh has achieved par excellence in academic field. He completed his master's degree from MDS University, Ajmer, Rajasthan, and obtained the prestigious PhD degree from Indian Institute of Technology in the year 2014. Presently serving as a principal researcher in Prayoga Institute of Education Research, Bangalore. Previously, he served as a research associate in MRIIRS Research Institute of Faridabad, Haryana for the year 2021 to 23, postdoctoral fellow in IIT Gandhinagar, Gujarat for the year 2017 to 20, and postdoctoral fellow in Imperial College, London, UK for the year 2014 to 16. He executed many research projects as a principal investigator in R&D IIT GN funded project, postdoctoral research in NERC UK and MOES India funded project, PhD scholar in 2 DST funded projects. He has published 37 research papers in highly reputed international journals with 680 citations, 11 H index, and 13 I index. With this brief introduction, I cordially invite today's eminent speaker, Dr. Ajit Singh. I once again welcome you, sir. Over you too, sir, and thank you very much.
Okay, please start.
Namaste, everyone. Thank you for the nice introduction, and thank you for the opportunity to speak today in this forum. I'm very excited to present this talk, Terrestrial Water Cycle through a River System. Before that, please allow me a moment to speak about my current affiliation, which is Prayoga Institute of Education Research. It is located around 40-50 kilometers south of Bangalore city center. And I've put a photograph of this building, which is based on Fibonacci sequence, which Fibonacci series, sorry. So it shows the kind of vision this institute has. So our institute is mainly focused on school education through experiential learning, and the program is called Kriya program, which provides opportunity to students to learn based on hands-on experience. Besides, we are also involved in Anveshna program, where we provide high school students an opportunity to work in labs or to conduct a research project. So they spend 3 months of time with us and do original research work during their summer times. And apart from that, we are also involved in domain research. We have a very experienced team of senior researchers who are focused in several research themes across, which includes life sciences, chemical sciences, material and nanosciences, and green chemistry is also one of the aspects. And of course, the earth sciences, which began around a couple of years back. Because one of the vision of the institute is that earth science education is very crucial and need of the hour, particularly for our future generation. So with this, I'll again welcome you all to this presentation. Okay, to begin with, the three foundational approaches, how the learning begins, depends on observation. First thing is observing the surrounding and qualitatively understanding it in terms of its system and components. The next step for learning is measurement. When we begin to measure things quantitatively, component of any systems, and we realize that it's not always possible to measure things or its a system or its component, then we move towards modeling based on our understanding of our measurements, conceptual understanding of the system. We try to simulate through models and try to understand any phenomena process in our surroundings. And this is how it relates with the theme of Prayoga, which is based on experiential learning, conceptual learning, and then applied pedagogy. Now, one of the aspects of learning is the systems approach. We try to identify systems at various scales in order to break down our understanding. So how do we define system? Is that system is part of the, it refers to the part of the universe on which we are making the observation, and everything else becomes the surrounding. And system can be open system, can be closed system, or isolated system, which is defined on the basis of whether energy or mass can be exchanged. So in an open system, there is exchange of energy, there is exchange of mass, and most of our ecosystems or living organisms comes under this category. Closed systems means there is only exchange of energy and there is no exchange of mass, whereas isolated system, neither of energy or mass can be exchanged. So this is a basic approach which often we adopt in earth system sciences. Now, talking about the major categories of earth system sciences, we have atmosphere, which mainly comprises of all the gases surrounding the earth. Geosphere refers to the solid earth. Then hydrosphere refers to the water in all its forms. But there is a specific form of water, solid water, snow, ice, which is identified as cryosphere. And then, of course, biosphere, which we all are part of. So these are the broader categories. Today, our focus is on hydrosphere, and the major components of system can be understood as reservoir, which stores the matter for a given time, and the fluxes when matter or energy transfers from one reservoir to other. Storages are again within the reservoir, what is the storage at any given moment. And when this happens in a repetition manner, this forms the cycle. For example, water cycle, carbon cycle, and nitrogen cycle, and so on. Now here is a cartoon example for Earth system, which is mostly related to water. So if we can think of these taps as input to the system, and if you assume these taps have different rate of input, so uh, depending on that, the water flow from the different inputs will be different. This tank here represents the storage, and at the base of this, there are different outlets, and depending on the nature of outlet or the rate these fluxes, output from this system will vary depending on which part we are focused on. Now, coming to the real world picture of hydrological cycle. So there are various components of landforms where water transport. So hydrological cycle basically represents the journey of water from one component or one system to the other, from atmosphere to the lithosphere to the oceans, and then back again to the atmosphere. And the major drivers of uh, this cycle are precipitation, or we can begin with evaporation when water from ocean evaporate into the atmosphere. And then through condensation, it becomes precipitation and falls back on the landform where it is stored in different component like glaciers. It will be stored for many years, then it will melt and stored in lakes, and then from lakes and rivers it will flow into the ground and back towards the ocean. Even groundwater sometimes reaches into the ocean. So this is how this cycle completes. Now, okay, so as you can see on the surface of Earth, there are different kind of landforms. So in glacier region, there are glaciated landforms, eventually which will lead into river system, which are also called fluvial system, lake storages, ocean. So basically the face of Earth, we can look into different type of forms. And when we study these forms, we call this discipline as geomorphology. So morphs of shapes of the earth, our landforms on the earth. So when we start looking into geomorphic systems, so there are several ways to look into geomorphic system. Uh, Morphological systems, cascading systems, process response systems. So basically, this is the same system, but how do we approach or we study these systems? Based on that, these different categories are identified. What part of system are we trying to understand? So if we look one by one into them, like morphological system, when we try to understand morphological properties or relationship between them. For example, if I say drainage basin, which means a part of land which contributes all of its water to a particular area, so that forms a drainage basin. So all the rainfall in that area reaches to a common pour point that makes a river system. So drainage basin begins in some higher uplands or higher elevations, for example, in hills and mountains. And from there, rainfall begins to accumulate, and those elevations gradually reduce. So when we say we increase drainage basin area, So what is the relation with the gradient? As we move down from elevation, we are including more and more lower elevation. So overall, river gradient will reduce. So kind of relationship when we try to understand between the different landforms. So we call this morphological system approach. Similarly, if we have to increase the stream gradient, we have to move towards the maximum slope, include maximum slope. Otherwise, so increase in gradient is related to increase in maximum slopes. So this is an approach for understanding systems. Another approach is a cascading system approach, where the focus is on movement of mass and flow of energies from one component to the other, like from atmosphere, rate of precipitation, how it fluctuates, how it can change the surface water, and then infiltration, based on infiltration of the surface water, how soil water, water in the soil changes. So here the focus is more on the movement of mass and energy. So in this picture, these arrows represent energies, and these bold arrows represent change flow of masses from one component to other. Another approach is to understand systems through process response. So now there are different parts of a system, and one process can lead to some changes in other component of a system, and how they respond to each other, how these processes reflect back to each other. So, for example, if we start with this figure on the left, if there is uplift of a landform, so in on Earth, there is always changes in the elevation. Sometimes these are sudden, sometimes these are very subtle changes. So let's assume there is uplift in maybe a Himalayan river. We can take example. So once there is uplift, overall river gradient, stream gradient will increase. And once the stream gradient increases, the flow velocity of water in that river will obviously increase. And what happens when water have more energy? It can do increase in the erosion rate, which means breaking down of rocks. So while traveling, river water can erode rocks, can break down rock material physically and sometimes chemically also. So with increased velocity, there will be increase in rate. Now, what happens? The increase in erosion rate will, so there is movement of material with the water. So ultimately, whatever landform has uplifted through erosion, it will again be brought back to its previous elevation or maybe some other elevation. But overall, there will be again change. So ultimately, what we started with uplift. So this process led to a negative impact on the initial process. So such a process response system is called negative feedback system. We can take an example where it could be a positive feedback, where with a storm event, sudden heavy rainfall or sudden cyclone rainfall can increase surface runoff. That can increase rate of soil erosion, and then since again this is erosion, but it will help in infiltration, and then so if soil removes, there will be negative impact on infiltration, water infiltration into soil. And then if there is less infiltration, there will be more surface runoff. So so this way, this process ultimately gives a positive feedback to the initial signal. So these are few approaches for which through which we try to understand morphological systems or geomorphic systems. Now, the most important thing is about looking into time and space. Depending on our observation time for which we are observing any process and at what scale we can define geomorphic systems in terms of its equilibrium. So, for example, if our observation time is very small, so the change in any landform won't be much. So it would be like static equilibrium. For example, if you look into flow rate of a river, so if you see a river in the morning and then again you go and see that same river in the evening, probably you don't see much change in flow, provided there is no rainfall. So in that case, you will see same kind of flow in that river or no changes. So we basically this x-axis represents time and y-axis represents any change in the space or elevation or flow, depth of the river water. In this case, you can say so depth of river water will be same. But if you increase your time of observation, so you will see that one can see that there are changes, but overall uh, elevation remains same. There are subtle changes. There will be time when there will be more water, but then there is time when there is less water in the river, or in terms of sediment or its elevation. There is time when river is eroding more, but then there is time when it begins to deposit as well. So there will be minor changes, but on a longer term, it is like in a steady state equilibrium. Nothing, so you don't see overall change. There will be fluctuation. But if you observe same phenomena for over a much longer time period, so you'll realize that this system is gradually going into change, which is a dynamic equilibrium. For a given time, there are fluctuations, but overall, the system from a high elevation comes to a lower elevation. So, for example, we know about several mountain chains, and we say Aravallis is the oldest mountain chain. And over the time, it has reduced. So, Aravalli is very old, but back in the time, it was same as possibly Himalayan mountain chain. So, gradually, the system evolves and its elevation reduces. So, so it depends on mostly on the time of observation. Sometimes changes are not regular. So few of the processes happens at a constant rate, but sometimes these changes are specifically in time. So overall the system will stay and then it shift to another equilibrium and then it stays there. So this type of are called dynamic metastable equilibrium. So these are the way evolution of understanding of geomorphology and the system approach looks into. So processes are same, but how we are looking into these. So these are like the framework, the background, how we look into any of the system. We will focus on, again, hydrological cycle. So here also we will apply a system approach. Why is it very important? So we will look into how we understand these different processes in the system. But first, what is the importance of hydrological cycle? So when we look into this uh, as a part of rock cycle, so we know one of the important aspect is sedimentary rocks. The component of rocks is sedimentary, and it is mainly dependent on this work of a river. So in higher elevation, river creates erodes the rocks to create sediment, and then it transport it into plains and then into delta, and it deposits there. So this is kind of work that this hydrological cycle is doing for the rock cycle. In terms of water chemistry, we know rainwater is pure form of water, but when it falls on the ground and infiltrate through soil, then its chemistry changes. Well, once it reaches from surface to the ground, and on even while traveling from in the stream, it its chemistry changes. So that part is also, that's why hydrological cycle also becomes important. Changes in landforms. So as we explained in part of rock cycle, so it changes the landform as well. And in all this process, of course, it is important for life form, as river not only carries sediment, but it also carries a lot of nutrients from one place to another. It provides substratum for a lot of life form on aquatic life form or near aquatic life forms. It provides substratum nutrition. So in that way, hydrological cycle has a diverse kind of importance to us. Again, looking into hydrological cycle in terms of numbers. So when we say there are reservoirs in terms of ocean, there are reservoirs in terms of rivers, in terms of groundwater. So if we look at the very first picture or in where we show the numbers, so when we look at ocean, it covers 70% of the surface area, and oceans represent 97% of the total volume of water on Earth. And on the other extreme, when we look into atmosphere, it represents very small amount of water, total water on the Earth. But we know atmosphere is such a crucial component of this hydrological cycle, and it is very crucial for life on the Earth. So what I'm trying to highlight is it's not the amount, it's role that it play for the sustenance of life. So that's why we are focused more on terrestrial water, which also forms very small amount compared to the amount of water in the ocean. So this slide, I mean, there is always a question, where did the water come from? I mean, on Earth, when it was evolving, where did the water come from? In what state we are seeing it today? It was not same as always. It evolved during its the history of Earth. So most of the internal heating and chemical reactions released water bound in minerals as oxides and hydroxides. And we also believe that through initially there were a lot of comets and planetesimals that brought water from across the universe on the Earth. Now again, here again showing the numbers in terms of storages and in terms of fluxes. So ocean, which represents uh, the maximum amount of flux, the values are in terms of thousands of kilometer cube. Uh, Again, this atmosphere is relatively very less, and major transportation between these happens through evapotranspiration and precipitation, and on ocean, major exchanges with atmosphere occurs through evaporation and precipitation. Then there is mean residence time. How much time this water spends in a reservoir, that also varies. So in atmosphere, it is very short. In few days, it will transport, or whether it will through precipitation, it will be transferred to land surface. In ocean, it's very long mean residence time, up to 3,000 years, and particularly in the deeper oceans. Again, river water flows at much faster rate, but when it comes to groundwater, again, so there are methods to test the age of water, and sometimes it could be as old as few tens of thousands of years. So what is important here is to understand that these flow rates are very different. And once we, through some of the human activities, if these rates are changed, so in a way we are kind of disturbing these flow rates, and It's not easy, like once some water is gone, it's gone for maybe years together. So that's why it becomes very important to understand these flux rates. One more question is, why does water move? So what is the source of energy for this system? Of course, major source of energy is solar energy, and Earth not being a flat surface, it's a rounded surface, spherical surface, and distribution of landform and distribution of water bodies is not uniform. There are oceans uh, spread and there is land continental spread, which is not uniform. So given all these, there is the heating of Earth is not uniform, which sets up the temperature gradients. And these temperature gradients allow air movement uh, from the high pressure areas to the low pressure areas. And with this, atmospheric moisture travels. And this is how basically evaporated water in the air transported from one part to the other. So when after rainfall, precipitation on the surface of Earth, it's in reverse, it's mostly through gravity. And when, so through gravity from mountains to ocean, this water flows. And once it reach ocean, again in ocean, there are ocean currents that allows water to transport across the ocean. So these are the basic drivers, but ultimate source is the solar energy for this system that provides power for movement of material across. Now, I will try to uh, focus more on where is the water or why we talk so much about the water on the land. So to begin with, particularly in the form of rivers or in the form of lakes. So again, I'm showing this figure. So what is interesting is that most of it is saline water and only 2.5%, which is this amount, is fresh water. But when we further look into this amount and we break down this freshwater distribution, so we have most of it locked in our glaciers. Then another major part is in the form of groundwater. So, so of course, in today's modern world, we are using groundwater a lot. But ideally speaking, groundwater is not readily available to us without technology. Our major primary source of water is surface water, which is even lesser in this case. So now, when we further break down this smallest amount of surface water, we see majority of water is in the form of lakes, and rivers is only 1.6% of this smaller percent water available. Then soil moisture water is again very important for vegetation across. Atmospheric water anyways is important, and then wetlands. So you can see rivers are very small part of this whole water in terms of amount of water. And that's why I have highlighted lakes and rivers. So somehow these figures do not give us a sense, because again with this smaller part we again make it a full pie chart and it looks like a lot of water, but in terms of percentage, when we see, it's like a very small percentage of water is available to us. So understanding these river systems, these lake system becomes very important. So and this is another picture which show another slide that shows with respect to the total area of Earth and total area of oceans and continents. Again, river forms a very small surface area. So basically, I want to highlight here is like we are dealing with a very delicate system, which is not very abundant, and so we should be aware about what we are dealing with. So this picture is to show major rivers across the globe. They are present But when we look into the total picture, it only forms 0.4% of the surface. So I think with this general idea and approaches to understand how we try to understand these systems, what kind of framework we used for understanding of water cycle. And now I want to present few of the examples from the research, what exactly is happening to the river system. So I have been mentioning about there is water in the river, there is sediment in the river, but so let's try to look into taking few examples, one from Ganga River, one from the Western Ghat. Then I will later on talk about lakes in the Bangalore and their role in water sustainability and how water quality of small river is changing. So these are very important aspects of terrestrial water system. So as I mentioned, observation is the first thing that we do. So in this picture, here it shows Ganga river system. And this is part of North India, and this across this red line, north of this red line is Himalaya. And this red line separates the Ganga plains from the Himalaya. So that's why this red line, we call it as a mountain front. And towards the south, then there is Bundelkhand Craton, which again has relatively higher elevation compared to the plains. And that's why there are few rivers that contribute water and sediment to Ganga river system. And these numbers across this basin, they represent the observation stations, we also call river gauge station, where measurements of amount of water, amount of sediment is monitored. So basically, this is observation. So when we look into the data, what kind of water flows through this? So most of these observations are very difficult, and the data um, resolution is not very high. So what we have here is annual data, annual flow rates of at these stations. But this will provide us a picture like how much water, how much sediment in different part of this basin, how much sediment each year. So the sediment means the landform. We are losing mountains through this river system. Every year, a lot of sediment eroded from mountains, transported through plains, and deposited in the Bay of Bengal. But what it looks like when we look into it in terms of numbers. So what is the observation here? And so again, let me explain these. So for the sake of convenience and to understand, this whole basin has been divided into like Western Himalayan, hinterland Himalaya, transitional hinterland Himalaya, and Eastern hinterland Himalaya. So Himalayan section has been divided into Western, Eastern, and transitional. Similarly, the plain areas, Western Ganga Plain, transitional Ganga Plain, and Eastern Ganga Plain. And this area is called Bundelkhand. So these are the major divisions, physiological divisions we have identified, and how sediment is transporting across. So this is a Sankey diagram which represents how material is flowing across the nodes. So nodes means these stations, and width of these segments represent the amount of you can say the flux amount of material that is being transported. So this part in the top, this represents Himalaya. This whole green region represents alluvial plains, and then the main Ganga channel, Ganga river. So you can see when we are in western region, we see very thin lines in here compared to the eastern region. So now we are getting a picture like there is more sediment flowing from this eastern end compared to the western. And as we come to the plain, the picture remains same. And then the main canal. So because here the width is relatively more compared to the main channel. So it gives us a sense like there is something happening in terms of erosion and deposition. And when we summarize this information in terms of sediment budgeting, so again, this whole figure represents the Ganga basin, and these numbers here represent the sediment amount of sediment that is produced in different part of this Ganga basin. So again, in western part, it's only 6% of the total sediment is generated when we compare it to the eastern part. So our observation basically leads us to the question or leads us to a hypothesis like what could be the possible reason why there are so much sediment generation in this? Is there more rainfall in this region, or this area is high elevation, or there are differences in vegetation? And when we move to plain area, this western Ganga plain is still a source of sediment. So this black represents source of sediment. So some of the sediment is still being produced in western Ganga plains. But when we look at eastern Ganga plain, then it becomes a sink, which means so much of sediment transported through Himalayan region or not all of it could be transported through the plains. Some of it is deposited in these plains. So this area becomes a sink. Of course, it's not a permanent sink. Of course, if there is a transient storage, ultimately this will lead to Bay of Bengal. Similarly, the main Ganga channel, MGT, is the main Ganga trunk. In this reach, it becomes a sediment sink. And ultimately, the flux from Farakka station, which is quite south before the Bay of Bengal, there is 52% of overall generated sediment each year flows through the Bay of Bengal. The rest of it is being deposited transiently in the plains and in the main Ganga channel. In comparison, whole of the Bundelkhand Craton produces 11% of the sediment that is being transported in the Ganga system. So this was a recent study that we published in Environmental Research Letter. And this was the major finding, like at a basin scale, what is the observation, how this system is functioning. Now I will present an example from Western Ghats looking into smaller rivers. So I will show you here. So when I say Western Ghat, that means all the western coastal plains, and then there is a elevated western front here from where very small streams flow towards the west. So these black lines represent drainage basins or catchment area of smaller rivers. Now, what is happening in this part when we look into, so from a larger Ganga basin, when we look into smaller basins and look into what is, how sediment and water transports in this system. So here is a very interesting way to look at it. So what happens if we plot water discharge, which is represented as Q, and sediment discharge as QS. So once you plot the observation for 1 year, like let's say for each month you have a value for water, you have a value of sediment that flows through this basin, and you plot this data, so you will get a scatter. But once we join the lines in terms of their time of observation through the year, so we get these loops, which so these plots are called hysteresis plots, and these loops, when we connect these lines based on time of observation, we get different kind of scenario. So these loops are looked at as like this is a rising limb and this is falling limb. Now, if looking at the arrows, in the initial part of year, there is rise in compared to water discharge and sediment discharge, there is an increase. Later part, there is a decrease. But there are other systems where rising limb could be lesser than the falling limb. So what it says is sediment discharge is more during the falling limb or later part of the year than the initial part. Sometimes it gives you a eight-shaped figure where it changes. Initially, there was a high rate of sediment, but then it reduces, and then again it changes. And sometimes there is no such a relation. And so these can be looked into in terms of how sediment is being moved into that system. So if there are some flooding events or sudden movement of sediments, that's where we get some kind of no hysteresis situation. Or for counterclockwise, if there is sediment generated, but transportation of sediment happens only after a particular kind of discharge, then you will see counterclockwise kind of hysteresis loop. And so in order to put a number to this, this is how basically HI, hysteresis index, is defined. So basically area under the rising limb and area under the falling limb, the ratio of this represents hysteresis index. So this is what basically is done for these smaller basins here. For each of the basin, hysteresis index is calculated. And for calculation, the data used was monthly discharge for a duration of like 20-30 years, for which data is available on through our Central Water Commission website. So it basically represents sediment dynamics for last 20-30 years. Now, so now we have H index values, but we want to see how these values change with respect to monsoon rainfall. So when we say monsoon rainfall, we are looking into the rainfall which happens during monsoon month from June, July, August, and September. And when we say rainfall seasonality is the ratio of monsoon to non-monsoon rainfall, so we see that there is overall some relation with the rainfall. The HI index increases with increasing rainfall. Then there are other parameters that govern sediment movement, which is vegetation, because if there is a vegetation that provides a cover and hindrance to sediment flow. And the way we calculate the presence of vegetation is using NDVI. It's a vegetation index based on its spectral across this region. And here we see a negative relationship between NDVI and NDVI seasonality. So HI index reduces with that. So basically, it's kind of highlight how vegetation or how rainfall is governing sediment movement across these basins. So similarly, then you can one can try to look into how land use, land cover, which means whether it's natural vegetation, natural forest cover, or whether it's a settlement area, built up area, how we are using that land. So in that catchment, what is the proportion of land use and land cover, and how these HI index, whether there is any change. So when compared with built up area and evergreen, so built up area represents land use and evergreen broadleaf represents uh, land cover. So there is not very strong relationship, but some kind of negative relation we can infer out of this. So this was another study looking into sediment dynamics in a smaller river for monthly observations. And we were able to show in this like how we can use hysteresis index indices. If we can calculate hysteresis indices for a basin, we can try to understand what is happening with this river sediment dynamics when there is a change in rainfall, when there is change in vegetation cover, and so on. So now I have come to a part where I thought it would be nice to represent some student research, and which is also relevant because this is mainly focused in Bangalore region. So these are the students who join us during Anveshna program uh, for during their summer vacations. So 3 months they spend, and they do a original research, generate a data, and come out with their own interpretations and own findings. So this was particularly interested. So when I joined Prayoga, gradually I learned that lakes are very important, and there are so many lakes across Karnataka. And since these were once back in the time, uh, these were more important for the water supply across the state, because the rainwater flows from one lake or tank, Rajakalwe, as we also call it. So this project was mainly focused on how we can think of lakes to be a solution for our water demand. So if we look at the water demand of Bangalore, so it is an estimate provided through one report in one study from, I think, Japanese agency. So demand against the demand, our supply is relatively less, and we can expect this demand to be increasing. And of course, provide this demand through Kaveri water supply as well. But this is the demand side where the demand is increasing. But when we look on the potential supply side, which is rainfall, so we see there is plentiful rainfall across throughout the year in Bangalore. And if we take whole of not just the Bangalore city, but Bangalore as a district, we take the area and multiply it with the average rainfall during a year, we find that around 11,000, or one could say 12,000 billion liters of water we receive in terms of rain. Not to say that all of water belongs to us, it belongs to every living organism on this land. But of course, this water supply, how much are we able to tap in terms of our lakes or in terms of our groundwater? So, it is like what is our demands and what is available. And so the question is, where can we store these waters? So basically, we see, if we can summarize in this, that there is plentiful rainfall, but rainwater storage, we are not sure whether we are able to store that much of rainwater for our needs or not. So in order to understand how much rainwater we can store, the students prepared lake map for the year 2011 and 2024 to look into how our lakes are changing over this time in terms of number of lakes, in terms of area of lake. And then we also wanted to know what is the change in the volume of lakes over this time period. So we can use digital elevation model through remote sensing and estimate depth changes in depth of the lakes, so overall change in the volume. So again, this represents topo sheets were used to identify lakes across the Bangalore district, not just the Bangalore city, but the Bangalore district and its rural area also. And then satellite images were used to look into the present situation of lakes. So the students very carefully marked all the lakes, each and every small lake. And in GIS system, once you draw all these lakes, you can calculate their number, their size, and also, as I mentioned, their volume. So this is again maps that represent how many lakes. Also, all these small polygons represent lakes, and in 2011, and on this map in 2024. So even through visual observation, we can see there are many changes across. And for your reference, this is the whole of this is the urban Bangalore. Bangalore city is somewhere here. and this is the rural Bangalore, and then our adjacent area, and this part covers some part of Tamil Nadu as well. So now when we try to look into statistics and we calculate number of lakes, changes in number of lakes. So this figure here represents changes in number of lakes in terms of area. So these lakes are smaller in area, so their number has reduced. And so we can see smaller lakes are more prone for encroachment and being abandoned, and they are almost occupied, and they are no more on the map of, they say, region. Of course, bigger lakes, there is not, of course, we don't lose it in terms of numbers, but in terms of volume, there is a loss in the overall lake capacity. So overall, uh, so this is where the volume losses can be seen. So bigger lakes lost volume, not in number, but and this volume loss could be for many reasons, like dumping of a lot of garbage and sediments and no desilting. So what this project highlights is that our lakes are good enough, but we are not taking care of these lakes enough to store the available rainwater, and then we are bringing water from Kaveri Basin, which is much costly. So this is to summarize, like this is the available rainfall water. This is the current capacity of our lakes, but original capacity can be reached, which is nearly not exactly twice, but much more than what current capacity is. So I'm not presenting the water quality results also, but because water quality wise also lakes are deteriorating in terms of water quality. But overall, this project was providing solution for uh, our water demands, how lakes can be sustainable. Sorry, is there a time of 5 more minutes? I can.
No problem.
Okay. So this recent study was focused on integrating surface water and groundwater interactions. So again, these are the students who spent this summer looking into a very small river which is close to our Prayoga campus. So this is a river. For your reference, this is Bangalore city up here, Banshankari area, and this is where the small Swarnamukhi river flows. And somewhere here in Ravgoldu is the Prayoga Institute located. And this is another big river, Rishabhavati. Ultimately, both these rivers meet to Arkavati River down south in near Kanakpura. So our focus was to look into this river system mainly because in this region it is Banerghatta forest, where we can expect the river to be in its natural form in terms of water quality. But close to this part in Harohalli region, there is industrial area coming up. So we collected samples across this river system. So these yellow dots represent the sample collection, and we also analyze for comparison well samples. So these shallow well samples. So how is the water quality in this river and compares with the water quality of these well? Is there any relation between the two? So this is where the focus was to look into a small river system and its water quality. So this is to show the experiments that the students conducted to measure trace elements and measure cations and anions and trace and heavy elements in the samples. And here I am showing all the major cations and anions. So in each of the figure, this represents upstream to downstream. All the samples are arranged in this area upstream, and then you go to downstream. For comparison, we have Rishabhavati sample and we have Arkavati river sample also. So overall, I mean, to summarize, the one thing is to compare it with the drinking water quality standards, how these parameters are compared with that. But overall, we can see that there is an increase in these parameters as we move from upstream to downstream region. In some of the cases, there are differences in well and in the river system, but in some other cases, these values are quite comparable as well. Then looking into the sources, so since this is an ongoing work, I thought it would be interesting to highlight the findings. So based on these several parameters, there is a water quality index, WQI, which what it does, it normalizes all these parameters and compares it with the WHO or BIS standard of drinking water and quality, and then give a summation value. And there is a table for comparison, water quality index, which is if the value is less than 50, it's a good water quality. 50 to 100 is still, it's a good, 50 to 100 is good, and less than 50 is excellent. And so as the water quality index increases, it becomes unsuitable. So if we look at this distribution, upstream well and upstream river values are still within the range of good quality of water. But when we move into the downstream mean values and maximum values, and this is mean value, minimum value, even the minimum value is beyond 100, which puts it into the category of poor drinking water quality. So, so with these examples, I wanted to highlight different aspects of water in terms of as a sediment carrier, in terms of how lake systems can be used for sustainability, and how important is to monitor the water quality. I think, yeah, and then this slide represents trace and heavy elements are also present, something like lead, very trace amount, but it's concerning that some of the downstream river samples showing presence of lead, manganese. Iron and aluminium could be natural sources, but this is an alarming data at the moment. We have to look into more details. And I think with this, I have to end this presentation, and this figure I have kept to compare how this natural river system from its source to its sink, it changes under human impact. So this is a natural state and this is under human impact. I thought to keep it on the thank you slide. Thank you so much for your time and attention.
Thank you very much for a very informative talk. Now there is time for some questions. Please, I request the members to ask one by one and brief questions, ask them briefly. So let us begin with Professor Rudraswamy. He wants to ask a question. Okay. Rudraswamy, you want to ask? Rudraswamy. Okay, you can unmute and ask.
Yes, sir. So, Dr.
Okay, please ask the question.
Ajit Singh, nice presentation. What are the concepts studied in geophysics subject? First question. Second question, how geophysics is similar and different as far as earth science is concerned. The third question, how geology and geography are different from each other? These are the three questions.
General questions he's asking.
Okay.
General questions.
Yes. So I will rather begin with the third question, like how geology and geography are different. Geography is a very wide subject, and the only part where geography study Earth is the surface of Earth, not beyond, below the surface of Earth, which is called physical geography. That is the common part with geology. Then there are, I know, few branches of the geography, which is political geography, human geography. So those, and there are many other branches of geography which are not common with geology. So it's only the physical geography that I know matches with the geomorphology part. And some of my co-authors are from geography discipline. Now, so that was the third question. Uh, First, the question was how geophysics can be used. So,
Yes.
based on physical properties such as electrical properties, magnetic properties, gravity or then material density property, explorations. In fact, in one of the did not include geophysical survey that we did in Lake Project to understand the subsurface. So, different kind of materials uh, uh, we can identify based on their physical properties, as I mentioned, electrical, magnetic, or any other density properties. So there is a branch, National Geophysical Research Institute. There is a lab in Hyderabad which entirely focused on exploration. So even groundwater exploration is done through geophysical surveys, and minerals exploration is done through geophysical survey. So these are the part where geology and physics come together, where physics methods and principle are used to explore geological systems. So I
Okay.
think it answers second question as well, how geophysics can contribute.
Thank you.
Okay. We want to Dr. Srikanta. I want to ask question. We can ask Dr. Srikanta. Srikanta, please unmute and ask.
Yeah. I have one this thing. This is with reference to hysteresis loop that you showed, no?
Yes, sir.
Regarding the sediment discharge. Am I right?
Yes.
Yeah. See, now hysteresis, as I understand from magnetostat, ferroelectricity. When I reverse the direction of magnetization, I feel that I don't get back the original magnetization. There will be some remnants and all that. Okay. Here, how do you explain this hysteresis as far as the sediment discharge is concerned? How does they come back? What I understand is sedimentation rate increasing, and then how do you again decrease it, and then it won't? What is that? How did it understand?
Apes of HI loops.
Yes.
Explain the different shapes. He wants to know.
Yes. So the way this data is
I thought sediment discharge is one way.
Wait. He will answer. Please,
okay.
he will explain.
Yes. So I will first explain what is the data used. So, for example, if you start, you have a river gauge station at a river. So you start your measurements for January, February, and so on till December. So for each month, you measure what is the flow of river, how much of sediment it is carrying, monthly discharge. And this data is for like a few years, tens of years. In this case, we had 20 to 30 years of data. Now, we know time-wise. So each year, January to December. So there is a direction for your data in terms of time. So when you join this line in terms of time of observation, you direction. So just imagine in first part of the year, January to May, there is too much of sediment being transported. But there could be a case where there is increase in water, but not in the sediment. It's only after the later part of the year there is increase in sediment flow.
That means after the rainy season, you mean the sediment rate will come down.
Yes. But
After the
yeah, that explains here counterclockwise. But in the case of clockwise, so it also depends on, so one thing is sediment generation and then its flow. And so once you prepare it, you know in what form this system is functioning, whether it takes time to generate sediment or sediment is readily available, and even with the very flux of water, it's transported. And later on, it's only the water. So you can see discharge is less here, but sediment supply is high. In this part, we have more water, but sediment supply is low. So this is how you come to know the system, how it is functioning, whether in this case, system is taking time to generate sediment. Once there is a certain amount of water available, then only the sediment is being evacuated.
So that sediment rate anyway depends on the rate of flow of water, right? I mean, is it?
Yes, so sediment generation, and then there are factors like what is the vegetation cover.
Also, time also involved. I will depict the time. Okay. We move on to other questions. Any other questions? So I have a few general questions. One of them is that why the oceans are so saline? What is the reason? How does one get such salty water? General question, one of them. And secondly, how does one get this ocean current? You talked about ocean currents. I can understand the air currents and all that. How the ocean currents are generated? Could you give some idea about that?
So both of these are very, very fundamental and very interesting question. Why is ocean water saline? Sometime back, we also had this discussion over lunch when some person, again from physics, she asked us, why is ocean water saline? So one obvious answer is like over the time evaporation of water has contributed to salinity. But then my colleague was exploring this. To be honest, I don't have a clear answer for this. And through evaporation over this time period could be a partial component, but ocean salinity depends on some other factor. But at the moment, I don't have an exact answer for this, but this is very interesting question. Sorry, he's not available right now to help me. So we will discuss this question maybe in future when we meet.
Ocean currents also can
Ocean current is something like there is one variation in the salinity. So if there is more evaporation in the shallow part, and salinity variations can create some kind of pressure differences for flow. So water from high salinity will flow to